All right, hello everyone. My name is Ran, and today I'm going to talk about RHYME, which is a multi-paradigm declarative query language. And so RHYME is a language that is designed to be to target JSON data, which is like hierarchical and nested. But the syntax of RHYME is very expressive, so it can also be extended to other style of workloads. And so, for example, tensors. Tensors are essentially also nested data. They are nested arrays, and they can we can target tensors that's either dense or sparse. And the language itself is originally inspired by some existing solutions that targets JSON data as well. For example, like JQ, JSON path, which is like JQ is very popular in JSON processing nowadays. And there's also GraphQL and xQuery, which exists like earlier, like used mainly for web applications. But since like JSON is a very widespread data exchange format nowadays, but like none of these tools like express tensor operations easily using their syntax. So we show that RHYME can we can express tensor operations and like queries from different style of workloads very conveniently. And the way tensor expressions are expressed in RHYME also closely has a close correspondence to einsum notations and most recently einops in Python. And we'll show that in just a minute. And RHYME is also inspired by functional array programming. So you do not write explicit loops, and we'll see in a second how that works. So let's start by looking at some core operations in RHYME, and we'll use the sample data set here, which is a JSON array that consists of an array of objects, and each object is essentially a record that contains some fields about country, city, and population. And so to access some nested field inside, we can just use path expressions, and this might be familiar. This is similar to how JSON path works, like when accessing nested values. So for example, we can do data.0.city to access the first element in the array and then the field city in that object. And we get Tokyo. And one unique characteristic of RHYME is that when you can also, the query itself is structured as well. So the query itself can also be nested. And to produce nested objects or arrays as a result, you can simply write the query as an object using the familiar JSON object notation. Like for example, we can construct the object with a single field called third, and then we can, on the right-hand side, we can have a path expression that accesses the second country value, or the third, which is because it's zero indexed. And we get the result with third, and the value is France. And so data processing requires some form of iteration to be expressed, and we do not write explicit for loops or while loops in our language. So we use the asterisk or the star, and we call it a generator. And JQ also have similar concept of generators. It basically produces a stream of value from a collection, and we use the star or the asterisk in the path to iterate the prefix collection. And for example, we write data.star here to iterate through data, which is the array which you saw. And then iterations is usually paired with some kind of aggregation or reduction. And so we can do this kind of sum operation that sums up all the values in the array. We do data.star population to get the population field from all the objects. And then we can count the number of values in that array. We can do max. And we use this kind of a bracket syntax to do array aggregation. Basically, we collect all the values in that stream and then put it in an array. And we can combine this with the object notation as well. We can construct an object with total and highest, and then we just put the corresponding aggregation on the right-hand side to get the result we want. And so, for group-by operations, which is also very fundamental in data processing, we can similarly just use object notations, and we can just, instead of having a constant key on the key side, we can just have another iterated value on the key side. For example, here we have data.start.country as the key, and then we have a sum of data.start.population, and this essentially groups the sum of population for each unique country value in the data set. And so we get, you can see in the result, we get the population, the total population for each country. And the way RHYME know that like this is the group we intend to do is that it will look at the generators that appears on both sides of the group-by operation, and we see the star generator on both sides. So we know these are the correlated expressions. So it will like infer that kind of dependency and then do the correct group-by operation. And we can also make these kind of iterations explicit by giving the generators a name. Like for example, we can use star A here to like explicitly tell that we want these to be correlated with each other. And these named generators also give us something else. They also unlocks like controlled iterations. We can use the name generators to express more like co-iterations. Like for example, when we have an anonymous generators, it is bind to the unique prefix. So for example, if data.start appears like twice or multiple times in the query, the semantic rule is that it will bind to it will like refer to the same iteration in the final generated code. And if we have data.start and other.start, then that means because there are different prefixes, so it will be like essentially be different loops in the generated code. And if like for example data.start and other.start they appear in a single expression, it will basically essentially like result in nested loops or Cartesian products in the generated code. But if we have name generators on like two distinct prefix like data.start A and other.start A here, it will actually perform a co-iteration on the two collections. And in the generated code, it will look something like this. So for all the star A value in data, it will check the existence on the other collections, and then if it does not exist on the other collection, we just continue. So this actually give us co-iteration and also inner join semantics for objects. And also name generators can be freely used in any expressions as well. For example, in the top right corner, we have this query. We build an array of objects, and the objects have posts, which we directly use the star A identifier here, and we get the index +1 to get the position. So it can be used as a first class identifier in the query. So what does all of these like RHYME, this syntax in RHYME gives us? We can see that we can apply these to tensor operations as well. Like for example, we have A and B, which are like two vectors, and then we can have a query which says sum A.star I times B.star I, and as we saw before, we have the shared star I in like following two distinct collections. So we basically perform a co-iteration over the two arrays, and then we multiply each value, and then we sum all the results. So this basically is just a dot product, and it gives us 5. And because we're like doing kind of an inner join, we only iterate on the key intersections of the collections. We like you can see that B, the last value in B is ignored, and we have we also have support for outer join semantics, or like where you can like actually give a default value if the shape does not match. But we do not like elaborate more on this in this presentation. And with the group-by operations using the object notation, we can express more complicated operations. Like for example, tensor transpose, we can look at the inner expression first, which is B.star I .star J. It essentially loops through all the values in the B matrix, and then the objects surround that expression is basically doing a group-by. So we first do a group-by operations on star I, and then we group by on star J. So in the generated code, it will look like result indexed by J and then index by I equals be indexed by j and indexed by I and j first. So effectively, we're performing a tensor transpose here. And this also is also closely related to INOP notation. So in INOP, we will write this as ij, and we're mapping it to ji. And so we can essentially perform like more tensor operations here. Like for example, the transpose we just saw, and we can do a sum of all elements, and you can see that they can all closely map to INOP operations. So we can essentially have an INOP front end that parses into rhyme expressions, and then it will generate the code. And real world example would be RMS norm here, which is used very commonly in LLMs right now. And so we first calculate the RMS, and we essentially calculate the average value of x squared in the x vector, and then we do the norm. And so we have start norm here, iterating both x and the weights together. And we collect the result into an array. And we also support deep path. So like when using the normal generator, we kind of have to know the shape of the data. Like we have to know how many nested levels there are, but we can use these kind of deep path, which is a special kind of generator to express shape-polymorphic queries. Like for example, for the data here, we have the field B in different nested levels, and we can just write data dot double asterisk P dot B to access all the B values in different nested level. And if we use the generator directly, it basically enumerates all the paths all the way from the roots to the leaves. And this also gives us shape-polymorphic queries on tensors as well. So we can do a sum of all values and then a dot product on two tensors potentially. And so RHYME, let's take a step back and look at how RHYME is actually execute the queries. So we start from the textual query, and we get the AST, and then we generate RHYME IR, which is a special kind of IR, and I will talk about that in a second. And eventually, it will generate JavaScript or C code that actually execute the queries. And there can also be optionally input types, and we will do type validation if that is provided. And so this is what the IR looks like. And on the right-hand side, we have the query, which is the same RMS norm query we just saw. And then in the middle, we have the queries. So we have the IR. And it is all dependency-based, so there's no explicit loop in the IR as well. And on the right-hand side is the generated code. And we also support typing, and we can use the same kind of object notation to indicate the type of arrays, objects, and any kind of objects. And we can also add tags to the types so that we know the sparsity of tensors. And since it's all about code generation, we can essentially generate code that we can do pattern match, or we can just extend that with an additional operation called mapmul to and potentially we can just generate the kusparse mapmul call. And this is some preliminary performance result we're getting. This is more focused on the C code generation, and it works on mostly a DB related workload, but it shows the C code generation can reach the same performance as the state-of-the-art compiled DB engines, and also on JSON data. Yeah, so that is about RHYME, and RHYME is open source and under active development, so you can feel free to take a look as well. Right. So everything I have to